Hello. Okay, so let's sum things up with yet another modeling presentation. Welcome. I'm Martin from Comenius University, and after this presentation you will come to terms with a kind of special approach to processing polygonal meshes. So on the image you can see that we're basically wrapping a surface with another surface. Let me get my pointer. So our problem statement is to wrap some mesh, some triangulation, with a surface whose triangulation we can control. And we basically evolve it towards it and create something that looks like this. Now, why would we want to do that? Well, the type of evolution this is called the Lagrangian evolution, because we're evolving individual vertices. We're tracking a single surface rather than an entire field. But why would we want to do that? In reality, shrink wrapping is used, for example, to wrap the six-pack of your beer so that it holds together and there's more stability. And it's also useful to wrap other things, you know, like electronics. And then if we want to test whether the electronic, when it falls, whether it will sustain some damage, we can do finite element simulations. With this method, we can actually generate the mesh that is necessary for these simulations. We can also use this for filling holes, and eventually it may be used as a tool for remeshing, so improving the quality of the mesh. So we managed to actually, first of all, propagate the target mesh's shape into the surrounding space using a distance field. And then, of course, we needed to use its gradient as well to drive the sort of advection process that's inside. Our requirements, of course, for the gradients to exist everywhere and to have reasonable computational time. We also managed to stabilize the model because of the numerical properties of it. Basically, the numerical method is unstable for certain sizes of triangular elements, when there's a lot of inhomogeneity between those elements, and we just use a simple scale-based heuristic to stabilize the evolution of a given input mesh. Now, to the SDF preprocessing step, we basically extract a so-called triangle soup, which is just a set of independent triangles, and we expand the bounding box of our target mesh into the surrounding space by an offset, generate a bounding volume hierarchy for fast searching through space, and then use this hierarchy to build an octree, which is only used to generate sort of uniform volume elements in space. It's basically, each node is subdivided whenever it intersects the mesh. And the intersection query is done using the AABB tree above. Now we need to create a grid where we define our distance field, of course with the given dimensions. And we set the exact distance values from octree leaf, cube of voxels, to the closest triangle. So we basically transform it to the index space of the grid and set infinity everywhere else. And this serves as an initial condition for the so-called fast sweeping algorithm, which basically sweeps across the entire grid 8 times and finishes the rest of the field. I mean, optionally we can compute the sign of the distance field using a flood fill algorithm, much like the paint bucket tool in MS Paint. Now, the mathematical model itself consists of, well, basically this nonlinear differential equation. On the on the left-hand side, you can see the velocity of the surface, and here you have the curvature term, where without the epsilon, it would be just mean curvature flow, so it would smooth out all the features and sort of shrink the surface into a sphere. The other term is the advection part, so that's basically leading the surface along a certain field. And then there's tangential movement, so that we don't have accumulating vertices in one spot. Now, the control functions that we used are pretty similar in the first and the third term. There's just a little inverted exponential sort of Gaussian. And the eta function actually also contains the dot product between the negative gradient of distance and the normal, the unit normal to the surface. So what it basically does is that it rotates the surface so that these two vectors align. Now, the types of tangential redistribution that we use are angle-based and volume-based. The first one is just homogenizing angles of adjacent triangles for each vertex, and the other one homogenizes little volume elements, sort of neighborhoods around each vertex that I will refer to later. The angle-based is the best one for us at this point. Now, to understand a little bit what the eta term does, here's a simulation on a test mesh without the square root term with the constant d. It just produces a membrane that stretches over non-convex parts, and with basically that's a sine part, it fills the non-convex region, so it goes inside the cavities. Now, we have to do a numerical analysis of our problem, so we just transform our smooth model into the setup with our initial surface, which is a triangle mesh. So we combine it and integrate over these little volume elements, or two-dimensional volume elements actually, that surround each vertex and basically cover the entire mesh. They will be referred to as covolumes. Now, we also discretize the Laplacian that's used in there for the curvature term, and we do that using a cotangent scheme, first introduced by Meyer and colleagues. Now, we put all that into a system of linear equations that has a diagonally dominant matrix. So all the terms that refer to the curvature are stored in the matrix, and the rest that refers to the previous time step is in the right-hand side. And we solve it using a custom-made BiCG stab solver, stabilized biconjugate gradient method for large linear systems. So by actually wanting to stabilize the model, we consider the requirements for the semi-implicit approach to actually be stable. So the simple heuristic is that the time step should be approximately equal to the square of the spatial step. So in our case, it would be approximately equal to the average measure of the covolume. So we adjust the scale of the evolving surface so that this condition is satisfied. Now we start with an icosahedral sphere with some subdivision level S and radius R, and basically this is what it looks like. And because the icosahedron approximates the sphere, we assume that the distribution of vertices is more or less homogeneous, so we just divide the number of, I can see that on the screen. We just divide the surface area of the sphere by the number of vertices, and that's how we get our scaling parameter phi. Now the question is, how many vertices does a recursively subdivided icosahedron have with subdivision level S? To answer that, we start with the basic number of vertices and edges for an icosahedron, which is 12 vertices and 30 edges, and then we solve this system of recurrence relations for the number of vertices. Now, basically we interpolate between two different values of the scaling parameter to achieve satisfactory results. Now, we tested the performance of the SDF algorithm for 6 different meshes. You can see that a lot of them, well, the most interesting thing is that the AABB tree construction is independent, of course, of the voxel size, of the voxel resolution. And we also did that for 3 different CPUs, as you can see. And we notice that in the table, the first part actually refers to processors with roughly the same clock speed. And the other one is Intel i5, which is approximately 1.5 times slower. Now, we also have 2 different setups, intrin and no intrin, and that refers to using C++ intrinsics or advanced vector extensions used for computing the optimal split position for construction of the AABB tree. Now, we also simulated the stability of our meshes. So we start with our test meshes, and we do that for different time steps and different scaling parameter values, phi. And we can see that we're able to stabilize the mesh, for example, by using a relaxation function for the tangential redistribution, the rho, in the second column. And also, well, basically, the graph shows how many time steps the evolution survives without collapsing. And we can see that when we're in that sort of region that's given by the heuristic, with the boundaries from maximum and minimum scaling parameter values, we're basically safe. And we also measured how close to the target surface is the actual resulting surface. So that's the distance to gamma. And we also did matrix for finite element analysis. For example, minimum internal angle per phase, maximum angle, and the condition number of Jacobian between unit triangle and the transformed triangle. So you can see that triangles that are really stretched have high values. Now this is what it looks like for other meshes for different subdivision levels. This is the distance evaluation. This is the minimum angle, maximum angle, and the Jacobian condition number. Now, there are other approaches similar to this, of course. The first one was done by Kobelt and colleagues, where he basically did a form of remeshing and corrected for the distorted deformed parts. Also, a similar approach was used for extracting brain images in tomography, and it's widely used in brain tomography as well. And then there's an article from Zacht and colleagues that basically creates a hierarchy of nested cages around a target mesh. So what's next for us? We want to refine the triangles during evolution so that we adjust for the stretched triangles, doing topology adjustments to mesh. We also want to do a little more better design of our experiments for stability simulations, optimize the ABB tree construction so that it's even faster, try evolving marching cubes isosurfaces, and also extend our method to quad meshes. So that will be pretty much it, and I'm ready for your questions.
I will start with the first question. What changes will we need for the extensions of quad meshes?
There's a method used by Medla and colleagues from the Faculty of Civil Engineering, which basically does the same thing for quad meshes. So the operator, the Laplace operator, can be extended to quad meshes. Basically, the co-volumes look the same. They go into the centroids of the quad, and basically the operator works in very similar way. So it's not that difficult to extend it.
Could you use this for UV parametrization? Like the sphere has a UV parametrization that is easy, and then you shrink wrap it onto the object?
Yes, the article with Kobelt in the other methods actually uses a similar approach. So you can see that the bunny above is actually made from patching up together different patches with some distortion. So that's how Cobelt and colleagues did it in 1999. So a very similar approach.
Okay, and then I would have another one. So you mentioned refining triangles during the evolution, and what would you use to determine where to do that?
Matrix, like for example, some difference between principal curvatures, where there's a lot of stretching, for example. But you can essentially do, well, you can weigh the probability that you want to flip a triangle or split an edge or something like that when you need it. So you basically have a scalar function on top of the mesh based on requirements that you need. So
Do you think it would be possible to use some kind of global geometric operation instead of local ones? So not just flips and...
well, the simplest global operation is to split long edges. So you have a threshold that I don't want the edges to be longer than 2 centimeters. So you just split those that are longer.
Yeah, well, what I'm thinking about is to identify an edge loop, especially with quad meshes, an edge loop or a face loop, and then extrude, split that loop in one step.
Yeah, it's possible, but it would require, like the topological operations are complicated in the fact that, you know, basically you can affect the results along the way. For example, if you do splitting, you know, you can also make your geometry worse. So this is something that requires further analysis, of course.
I see, thank you.
No more questions? So let's thank the speaker again. And